All right, here's our second lecture. I am recording this, even though I said I was only going to do the first lecture recorded. The reason is because California is going through rolling blackouts with the heat wave and all these fires. And some students have reported having internet problems because of that. So I will probably go ahead and post this one as well. I think the heat wave is supposed to break over the weekend, so I will provide the recordings for the first week, and then after that, you are on your own. The last I heard from the distance learning team is in order for you to record the Zoom meeting as a participant, I have allowed that on the general settings, but in order for that to happen, I have to click twice for every student who records. I have to click more and then allow record every time someone tries to record it. That's just impractical, and it's really stupid for Zoom to require that. So the only way after this week you can actually get recordings of our lectures and labs is if you record them yourself. You either use your cell phone and record the video on the screen of your device, or you get a voice recorder and just record the audio, which is basically what happens in the live class anyway. In a live class, I do not allow video recording. I only allow audio recording. So it's no different from live. Okay, so let's go ahead and rejoin the PowerPoint. We got through a few principles in the first lecture. We talked about how... Everybody be sure you mute yourself. Go to the bottom left, click mute. Also make sure, unless you have talked to me, that your webcam is on. That's on the video tab just to the right of the mute button. Zoom actually changed their settings from last semester, and I think that is probably one of the 10 most stupidest things to do during ERT, when all of us teachers are having to learn at least 4 learning curves a day, and then we only use one of them. Well, now Zoom has changed everything. It used to be automatically muted as soon as I start a meeting. It is not. You have to mute yourself. Okay, where was I? Oh, well, we covered in the first lecture, we talked about the syllabus in the course. We talked about how human beings fit into the world of biology. We talked about some anatomical principles, anatomical positions, directional terms, body planes, and then body cavities. And then we finished up talking about the membranes in the anterior cavity. And I think we ended up on this slide, did we not? Okay, so everybody's there? We all on the same page now? Remember that the membranes are named. Their last name is based off the specific anterior cavity. That's number 1 on the slide. And then the first name, there's only 2 possible first names, either visceral or parietal, depending on if it's stuck to the organ or lining the cavity wall. Okay, pretty simple. All right, let's continue on talking about biology. And we have to talk about the cell. Now, in this week's lab, we're looking at pictures of cells and tissues. It is a lot better when you actually are able to play with a microscope and physically, realistically, authentically look at cells in a light microscope. Now you're just looking at pictures, but when we look at cells, we can see the outer border, which is the plasma membrane. Most cells, not all cells, like Tuesday lab, you found out that in blood, red blood cells don't have nuclei, but most cells have a nucleus in the center. That's where all the chromosomes and genes are. That's usually the largest organelle, and we will go over organelles a little bit later. And that's usually in the middle of the cell. And then we have the jelly in between the nucleus and that plasma membrane. And the word cytoplasm literally means cell jelly, but it sounds a lot more educated if you call it cytoplasm. Okay, now we're gonna look at organelles of not only the nucleus, but also in the cytoplasm next week. But first, we need to talk about the plasma membrane. And the reason why we need to talk about this is that not 100% of you are going to be taking physiology. And so some of this is basic parts of the course of anatomy that we want to cover here. This first note here on number 1 is I'm going to do, just so that you can understand the plasma membrane. Otherwise, these are just words and you're not going to know what they mean. I have to cover some basic chemistry. On that note, for those of you who are planning to take physiology, even though it is not a prerequisite, I'm going to tell you to treat it as a prerequisite. Take at least intro to chemistry before physiology. This college does not care about you, regardless of what the president says on camera. If they did, they would require chemistry as a prereq, and we are the only community college that offers human physiology without a chemistry prereq. There, I said it, and it's on a Zoom recording. So definitely do that, okay? Because to understand a lot of things like in human physiology and how the body and cells function, you have to have just a minimum working knowledge of chemistry. I'm going to give you one right now, and it won't take long, okay? First, we have to look at an atom. So before we do that, let's go ahead and take a look at the periodic table of elements. Now I'm going to need, I got an extension cord. And I'm going to try to get this as close as I can. Camera go off? It did go off. Well, let's see if I can fix this. There we go. Is that close enough for you?
That was good.
Okay. Now, if you look at the PowerPoint, even though I got it off right now, there are 3 basic subatomic particles. There's a lot more than that, but let's just start with that. In the center of the atom, there are 2 particles that have mass or weight. There are protons, and they have a positive charge, and neutrons. They have no charge. Okay, so let's look here at sodium up here. The blue number is the number of protons because an atom is defined by the number of protons. If it has 11 protons, it's sodium. Even though it says Na, that's from the Latin word for sodium. You round off the red number, that's 23, and that says that together protons and neutrons have an atomic weight or mass of 23. Well, since there are 11 protons, that means there are 12 neutrons. Add them together, it's 23. So far, so good? Because this is basic. This is just adding 11 plus 12. Okay, that's in the center. Now, not having any mass is electrons. And electrons are orbiting around the center of the atom in these orbital shells. And these are the black numbers, and they're tiny. So I got to hold the camera up here. I want you to look next to argon with 18 protons. And it says 288. Does everybody see that? Yes. 288. What that means is that the atoms are orbiting around the center of the protons and neutrons. And the inner shell, and this is an oversimplification so that you understand this, it actually isn't like this, but the inner shell can only fit 2. That's the 2. If there are 2 electrons there, it is full. Okay? Then the next shell can fit 8. If there is more than 8, it's got to go to the third shell outside of it. So what I have on the whiteboard there is oxygen. If you don't trust me that that's oxygen, here it is right there. 8 protons, and if you round that red number out to 16, there's got to be 8 neutrons. 8 plus 8. That is oxygen. Everybody see that? Then to be electrically neutral, there's got to be 8 electrons. But the inner shell can only fit 2. Then the remaining 6 have to be in the second shell. That's out of the 2, 8, 8. Is everybody following me? Okay, now in physiology, this is a good example. Information builds. If you weren't paying attention 2 minutes ago, none of this makes sense. Okay? This is oxygen, based off the numbers off the periodic table of elements. Now, let's go back to the PowerPoint, now that we have that. Okay, so there's the 3 basic subatomic particles. There are more. And I kind of just put this up here on the whiteboard as a reminder. Protons and neutrons have mass. And I'm trying to use the same colors that's up on that periodic table in the room. And then the black numbers were the electrons, but it wants to be in the 2, 8, 8 arrangement. Okay, so we covered that. This is basic chemistry. Now there are 3 types of basic chemical bonds that put atoms together to form a molecule. The one that is highlighted there, or emboldened rather, is covalent bonds. Covalent bonds means electron sharing, okay? Table salt is an example of ionic bonds, where sodium and chloride, one has a full positive charge, one has a full negative charge, and opposites attract. That's not what we're talking about here. All right. Now, the other thing about the 2, 8, 8 arrangement is that is where an atom has its lowest activation energy. Does that make any sense to anybody here? That's why you got to take chemistry. Let's see if I can explain lowest activation energy. One of the things about an introvert is an introvert never wants to be in front of a classroom, and I'm a very strong introvert. This is one of the good things about ERT, is that there's nobody's eyes are looking at me. But then I have to be on camera, and if you have your webcam on, then I am still seeing your eyes. So that makes me very unhappy as an introvert. But I do this because I do it for you. Okay, I'm not doing it for me. What does lowest activation energy mean? Because I'm doing this all day long, when I get off work, I want to go home and not speak for a while because I don't like the sound of my own voice. When we get to the lectures in the semester, it might be 10:30 and I might have covered everything in the PowerPoint, and I'll say, is there any questions? And I'll cut off the Zoom meeting at 10:30. I don't like hearing myself talk. I'm just not going to keep talking at 10:50 to hear myself talk. Everybody got it? So when I come home, I don't want to talk for a while. I get a big bucket. It's a large glass. I fill it with ice, and then I fill it with Pendleton Canadian whiskey. I sit on the couch, and I put my feet up, and I'm at 288. That's the analogy of an atom. When an atom is at 288, the atom is happy. Doesn't want to move. It's good. Okay, are we following 288? So when oxygen only has 6, it can't get to 28. With an atom this small, it's only going to go 28, not 288. And that's why oxygen always forms 2 covalent bonds. So it could be on the Barca Lounger with a bucket of Pendleton Canadian whiskey and not talking. Now, if you look at the periodic table of elements, and I don't know if you could see it from over there, but if you look at the far top left, that's hydrogen. It's got a blue one proton, and it's got a red one, which means no neutrons. All hydrogen is a proton and an electron.
Make sure I got this.
So what have I drawn on the whiteboard? And oxygen is happy, 288, or now 28. What have I just drawn on the whiteboard? Somebody say it.
Into something.
It's water. 1 oxygen, 2 hydrogen. Now the whole thing is neutral. It's not a charge. It has 10 total protons, 10 total electrons, no charge. When an atom or a small molecule has an unequal number of protons and electrons, that's when there is a charge. This is why sodium that has 11, okay, if we're talking about wanting to go to 288, in the case of sodium, it's 28, it's got 1 extra electron out here, and you put it in water, and it tosses out that electron so it could be at lowest activation energy. When it loses that electron, it becomes an ion. This is the term ion. It has 11 protons and only 10 electrons, so it's +1. Chloride. If you look at this, that's probably going in more detail than I need to, 17. If you put both of these atoms in water, chloride's going to have 2, 8, and 7. And it's going to want to pick up that electron. And now it's going to have 17 protons and 18 electrons. That is also an ion. When you put both of these in water, they become ions. When you evaporate the ion, they don't transfer that electron back because they're happy. And so one has a plus charge, one has a minus charge. They get really close together. That is an ionic bond because they're 2 ions. Everybody get what ions are? Now look back at the PowerPoint where it says ionic bonds. It's not emboldened because I'm not really talking about that there. But that's why table salt is an ionic bond, okay? All right. Now, if you look at the structure of oxygen here, oh boy, I'm working really hard. Okay. In physical chemistry, we can actually measure the angle between those 2 hydrogens, and it's about 100 degrees, which puts the 2 hydrogens, the 2 positive protons on one side of this neutral water molecule. On the other side, it's completely negative, nothing but electrons. The symbol for slightly is this. That's slightly positive. That's slightly negative. The whole thing is neutral, but this is how I'm going to define these terms for you so that you can understand them. If you can a North Pole, if you can discern a North Pole to be different from a South Pole, that is polar. That's the easiest definition I could give you. If you can discern a North Pole, in this case slightly negative, that is different from a South Pole, this is slightly positive, it's polar. Since water is polar, everything that is polar loves water. The Greek root word for love or brotherly love is philos, like the city of brotherly love, Philadelphia. Greeks have like 6 different words for love. English only has 1. But in this case, since things that are polar love water, we call it hydrophilic. Does this help at all? A little basic chemistry. This is why you guys got to take some chemistry. Now, let's look at carbon. Carbon, this is why it's really hard to do this when you're not in this whale room. A C, the big C, has 6 and 12. Anybody see that? That's carbon. A lot of you here are going to end up having to take organic chemistry. Organic chemistry is about the chemistry of carbon. Has nothing to do with your groceries. All right. So if it's 6 and 12, that means it has to have 6 protons and 6 neutrons. There's your total 12. In the 2,8, we got 2 electrons in this inner circle. That leaves only 4 in the second shell, which is right in between 0 and 8. This is why organic chemistry is a topic, because that puts this in a unique spot in the periodic table of elements. But if we do the same thing we did with water, we have to add 4 of those electrons to get to 2,8. And what I've basically drawn here is this. By the way, carbon always forms 4 covalent bonds. Oxygen only forms 2 covalent bonds because of the 288. Okay, this is why. And that's why the periodic table of elements is set up that way. Everything in that column with carbon will form 4 bonds. Everything in that column with oxygen will form 2, just so that you understand why that works that way. Okay, can anybody tell me what CH4 is? It's methane. Can anybody tell me where you find methane? Well, why don't you have a cheese and broccoli burrito? And in about 6 hours, you'll find some methane. Yeah, your gut bacteria will take that and make a lot of methane out of it. And that's a good proportion of your intestinal gas. This is in your farts. Okay. Well, oh, by the way, that's why you can actually light your farts. Please don't do it. I don't want you to sue the college because you burned your ass trying to test this out. All right, so don't do it. Now look at this thing, and I'm not going to write it all out, but this is tied to the other side, and before I'm done today, I'll put the camera on all sections of the whiteboard. Can you see a North Pole that is different from a South Pole in methane? You can. If you can't, I'm not going to write it all out, but you know it's tied to water over there. It is nonpolar. Now I drew this two-dimensionally on the whiteboard as symmetrical. In reality, methane is symmetrical in 3 dimensions. It is completely symmetrical. And since things that are nonpolar don't like water, they actually fear water, like a phobia, we will use the term hydrophobic. Okay? If you want to see your own little demonstration of this, take out some salad dressing out of your refrigerator. If it is Italian salad dressing or oil and vinegar based, it's in 2 layers because the vinegar is hydrophilic and the oil is hydrophobic and they don't mix. Before you put it on your salad, do you go ahead and just shake up the bottle? Then you can get them to mix, right? No. The only reason why you think they mix is because your eyes suck. You just made the bubbles really small. They actually don't mix. All right, you're going to see why I'm going over this in just a second here. I have a reason for doing this. Okay? Now, not only is methane nonpolar hydrophobic, I can extend this hydrocarbon chain to a really long chain, what's called a fatty acid, and the whole thing is nonpolar hydrophobic. Same thing. Notice in this what I've drawn, each carbon, each C, has 4 lines coming out of it. Each H, or hydrogen, can only have 1. When they're sharing an electron, that 1 goes to 2. 2 in the 288 is good. 2,8 in the 288 is good. 288 for the larger atoms is also good. That's the point of lowest activation energy. All right, now I think I covered these topics. I covered covalent bonds. This is sharing electrons to get to 288. And I've just covered polar hydrophilic and nonpolar hydrophobic. Everybody see what I'm doing here so far? Everybody understand polar and nonpolar? All ions, by the way, are polar. A little later, I'll go over the 4 biologically important macromolecules. Okay, but that'll be a little later because I think you might be ODing on chemistry right about now. Okay. The basic chemical, and it's a biologically important macromolecule, that makes up these cell membranes, the plasma membrane, is this thing called a phospholipid. Now, a phospholipid has a phosphate, which is an ion, a phosphate containing head, and because it is an ion, all ions are hydrophilic. And then it has 2 of these long tails, 2 of them. And like it says on the whiteboard, those hydrocarbon long chains are hydrophobic, nonpolar. You throw a whole bunch of these in distilled water and it's going to form this. And the reason why is because the water-loving hydrophilic heads want to be against the water outside the bubble and the water inside the bubble. And the water-fearing hydrophobic tails turn in on each other, forming a double layer, what we call a phospholipid bilayer, or lipid bilayer for short. Now, that's the reason why I had to cover all of that is so that you know why those heads want to be against the water and why those tails want to get away from the water. So if you look at any model plasma membrane that will look like this, you can see it's dominated by the phospholipid bilayer. In this picture from the internet, it is the polar heads are the blues, and the hydrophobic tails are the reds, pointing in on each other. It's a double layer. Everybody see that? Phospholipid bilayer has the consistency of salad dressing. Okay, now next to this slide, you want to write these notes down because I'm going to give you the 5 components, the top 5 components of a plasma membrane. And it's on this figure, but you don't know what they are yet. I'm going to tell you. There's more than 5. I'm giving you the top 5. Are we clear? First, number 1 is what we just covered, the phospholipid bilayer. There it is right there. Number 2, notice the word that's common to all these purple boulders is protein. So 1, phospholipid bilayer. 2, protein boulders. Call them protein boulders. This will help later when we talk about HDLs and LDLs. Proteins are dense, like rocks. So call them protein boulders. I don't care. Okay, that's 2. 3 is these yellow guys, 4-ring yellow guys called cholesterol. All membranes have cholesterol in them. 4, cytoskeleton filaments. They attach to some of these boulders, they attach to structures inside the cell, and voila, a cell membrane doesn't have the consistency of salad dressing. Otherwise, you'd be sitting in your chair at home, a dripping pile of goo. But that's not what you are because of cytoskeleton filaments. That's 4. And then 5 carbohydrate groups on the outside. See, this is extracellular environment. This is outside the cell. These are used as recognition groups. Down below is inside the cell. Okay? That's why it says cytoplasm inside the cell. Everybody got it? So far, so good. Any questions before I go on?
I'm sorry, I missed, what was number 5 again?
Carbohydrate groups.
Thank you.
On the outside of the cell, used as recognition structures. Okay. The plasma membrane has, as one of its characteristics, selective permeability. Selective permeability simply means some things go through easily, other things go through but with more difficulty, and other things never go through. And you can see it in this animation. Okay? You can see that some things that are small and uncharged, can go through easily. Other things can go through, but with more difficulty. It's got to find the right protein channel. Other things never go through. Things that are small and uncharged can go through the lipid bilayer. Boom. Other things have to go through the right protein channel, that one. Other things never go through. Now look at this animation right down the center of it. Out of those 5 things that I gave you, you only need the top 2 to show selective permeability. You should probably write that down next to the slide. This is part of the 2% that's not going to be highlighted, underlined, or bolded. You only need the phospholipid bilayer and protein boulders, the channels, and you can show selective permeability. Cholesterol, cytoskeleton filaments, carbohydrate groups don't contribute to selective permeability. You only need 1 and 2. Everybody see that? Okay, let's see if I got any, I got a little room right here and I'm gonna use this.
So the ones that you need are the protein boulders and the crystal skeleton.
Nope. Let me say it again. I gave you 5 in order. Did you write down them in order?
Yes.
You only need the first 2.
All right, that makes sense.
Phospholipid bilayer and protein boulders. Now look at this animation. What do you see going down the center? Just the first 2. You don't even see cholesterol. You only see phospholipid bilayer and protein boulders. That's all you see. All right. Now this is our first function slide. Again, because 100% of you are not going to have to take physiology. Function, anatomy is about structure, physiology is about function. Since not 100% of you are going to be taking physiology, you can almost guarantee function slides are going to be on the test. The functions of the plasma membrane is physical isolation. It separates inside the cell from outside the cell. It separates intracellular from extracellular. Because of selective permeability, this is where selective permeability is tied to this, it regulates what crosses. Generally, nutrients go in, waste products go out. Because of the carbohydrate groups plus other things, the plasma membrane also has sensitivity to both touch and chemicals. There's going to be some other structures we're going to talk about later when we jump from cells to tissues. We're basically going up through that biologically, the biology hierarchy of structures, getting bigger and bigger. So when we go from cells to tissues, we'll talk about structures that give plasma membrane structural support. Okay? All right. What I drew on the whiteboard is basically this. You need to know that any liquid mixture is called a solution. The liquid itself is called solvent. In biology, in our bodies, it's always water. And then the stuff in the water is called solute, whether it's ions like salts, sodium chloride, or glucose, or oxygen, or CO2. That's solute in the water, okay? So can you kind of see what I drew here in that tiny little picture, so I don't have to jump back and forth? It's basically the same thing that's what's on this figure. This is what you just need to know. All right. When we talk about transport processes, and this is what I'm going to finish on today's lecture on, and I'm giving you, pay attention because this is covered in a little bit more detail in physiology, okay? So if you pay attention to this, it'll make lecture exam 1 in physiology a lot easier. Now we have to talk about relative concentrations. Here we have the high solute concentration side, we have the low concentration side. When you have differences in concentrations of solute here, again, the stuff in the water, this is called the concentration gradient. And gradient is like a slope, like it says right here. It's like a slope. You got high to low concentration. Everybody see that? Same root word for the Cuesta grade or the Harris grade. It is a slope. Okay. Now, this will be very easy if you keep this in mind when we talk about active versus passive processes. If you are in a car on 101 and you want to go up to North County, San Luis Obispo, you have to go up the Cuesta grade, and your car has got to burn some gas to get up there. That's an active process. It would be extremely dangerous, but if you are on Cuesta Summit, you can turn your engine off and coast to San Luis. That's passive. Everybody got it? So if you're going uphill, you got to burn gas. If you're going downhill, you don't. Just that's the easiest way to keep this straight. Okay? Any questions? We will cover this a little bit later, but the gasoline for cells is a thing called ATP. All right? All right. So we're going to start out with passive processes. And with this, guys, I'm using this 15-foot USB extension cord for the first time. Hopefully this is a help and not a hindrance. Okay. So we are going to do passive processes first. When we talk about diffusion, this is about the solute. And it says like P, because everyone here can demonstrate diffusion simply. You just go to your sit-down toilet where you're pissing in a bowl and you aim your P to one end. That end is going to get really yellow. That's the high concentration side. On the other side of the toilet bowl is the low concentration side. And in very short order, it becomes uniformly yellow. That's diffusion. And it's like these purple dots. You pee in that lower left corner, it spreads out from high concentration to low concentration. If your pee is purple, you should go to the hospital. Okay. So you got diffusion. And this is going to be about solute. Going from high to low. Most passive processes are going from high to low. Going downhill. And it's going right through the lipid bilayer. Okay, so this the larger animations on the slide is showing you the balls are going right through the lipid bilayer, even though it's very short and doesn't cycle. Everybody got it? Now, osmosis is very similar, but in this case, it is not about the solute moving, it is about the water moving. And it is going from high to low. But it's going through the lipid bilayer. Now, watch this animation because it doesn't cycle and it's over really quick. But notice the green balls. Okay, what you want to write next to this slide is this. In order to see osmosis, you need two things. In order to see osmosis, you have to have two things. You have to have a selectively permeable membrane, that's one. And two, you have to have a solute that can't cross it.
Can you please repeat that?
You need two things to see osmosis. One, a selectively permeable membrane. And two, a solute that cannot cross it. Then the only thing that can move is water because it is small and uncharged. Everybody got it? Now look at this picture. It's not moving right now, but look at this picture in the middle of this slide. Right down the middle is one, a selectively permeable membrane, and two, green balls, solute, that cannot cross it. Those little tiny little winged molecules is water. They drew what I basically drew on the whiteboard way over there on the left. They are tiny, they're small and uncharged, and they can cross. So now, watch this now. Look at the screen. You're going to see the green balls bouncing off the selectively permeable membrane, and only the tiny winged molecules are crossing it. Everybody see that? Now you can see osmosis. Look at it again. Okay? Does anybody need for me to repeat anything? Okay. The other thing you might want to write next to the slide is a common saying that is used in clinic floors to keep you straight about which way the clinical manifestation is going to be. And that is water follows the salt. It's commonly said, water follows the salt. The reality is that water will follow anything that is osmotically active, like glucose. Water follows the glucose. That is the issue with poorly controlled diabetes mellitus. There's too much glucose in the blood. It spills over into the urine and it attracts water. Don't write this down. I'm just giving you medicine. Single word diabetes means you pee all the time. So you're constantly thirsty and you're drinking all the time. It goes right through you because you pee all the time. And then you're constantly thirsty. So you drink all the time. It goes right through you because you pee all the time. That's single word diabetes. Diabetes mellitus is a specific form of diabetes caused by water following the glucose. Does this help attaching it to clinical things?
Yes, yes.
Also, say you go to the physician and your blood pressure is high. Maybe not terribly, but kind of high. They go, oh, I think I want to recheck this in 2 weeks, come back. But in the 2-week time, cut out salts out of your diet. You might have too much salt in your diet. You cut out salt, you come back, and your blood pressure is normal. Why is that? If you are eating too much salt, there's too much salt in your body, in your tissues, and in your interstitial fluid is what it's called. And in your kidneys, water follows it out of the tubules back into your body. Instead of peeing out that water, you hang on to it because water is following the salts. Okay, and if you put too much water in the pipes in your house, your water pressure goes up. If you have too much water in your pipes, in your blood vessels, your blood pressure goes up. It's that simple. Okay, it's all on osmosis. Okay, so if you look at this figure, look at it. It has more salt, if that salt is the purple balls, on the right. Look how the water is following it to the right. And it's going to lift up the right side until both sides are equal. That's called equilibrium. Everybody got it? Any questions? Oh, by the way, in physiology, we talk about this. What do you think it takes to lift up a column of water against gravity? What does it take? You don't have to think like a physician, think like a plumber.
Pressure.
pressure. That is why this is called osmotic pressure. That's the only way you can lift up this column of water from this level to this level. Okay. One last clinical element to this, because this is something that you should know, and that is these three terms on the bottom of this animation. These three terms apply to the fluid or solution outside the cell. And it's talking about how much solute is in that solution outside of the cell relative to the cell. Hypertonic means there's more salt than inside the cell. Hypotonic means there is less salt than inside the cell, or less solute. Could be anything osmotically active. And iso means same. If you wear contact lenses, your wetting solution is isotonic. Otherwise, you're unhappy. Now, what happens when we drop red blood cells into these three solutions? There is more salt in the jar in hypertonic solution, so water follows it out and the cell shrinks. Now, when there's no solute, like say in distilled water, there's more solute inside the cell. Water follows it in until it pops. If you put a cell in isotonic solution, water is moving, but water in equals water out, and the cell remains the same. In hypertonic solution, there's more salt in the jar. Water follows it out, and the cell crenates because of loss of water. It shrinks and looks spiky. But if you put it in distilled water, there's more solute inside the cell. Water follows it in until it pops, called hemolysis. If you put it in isotonic solution, there is water moving, but in equals out, and the cell remains a biconcave disc, is what we call red blood cells. Everybody got it? Is this helpful?
Definitely.
Okay, filtration is a little bit different. Now let me just go to the whiteboard here, because I'm keeping track of passive, and I'm going to put over here active processes. And I'm going to go back to that animation that showed selective permeability, that small and uncharged thing, like water. It's going to the lipid bilayer. Diffusion and osmosis is examples of that. Filtration is not, and I'll tell you why. It says on this slide to think about it as in terms of a drip coffee maker, because the filter, the coffee filter, is doing filtration. In your bodies, and when you think about the drip coffee maker, that's driven by gravity. In your bodies, it is driven by blood pressure, okay? And both solute and water is leaving the capillaries because of blood pressure. This, in this case, this is not about going from high to low. It's being pushed out by blood pressure. It's not about concentration gradients, and that's why under passive processes, I say mostly high to low, because this does not apply to filtration. The reason why it is listed under passive processes is because the cells doing the filtering are not expending cellular energy to filter. They're not burning ATP. Here's ATP for passive processes. I put a line through it. These do not require ATP. And the cells doing the filtering are not expending ATP to filter. Now, just so that you know whole body reality, the cells, your left ventricle, that are generating the blood pressure are burning a ton of ATP to generate blood pressure. But the cells doing the filtering infiltration are not expending ATP. That's why it's listed under passive. Does anybody need any of that to be repeated? You got it? Okay. And you could see here, it's about what happens in all capillaries. Filtration happens in all capillaries. Stuff leaks out because of hydrostatic pressure, blood pressure. But what happens to water pressure if your pipes leak?
Goes
It
down.
Goes down. And that's what happens here because capillaries are leaking by filtration. That's going from 36 here to 15. Now look at this. I already talked about this. Osmotic pressure is all about drawing it in, and it's constant. And now all of a sudden, these numbers exceed this lower blood pressure and stuff is now going in. So nutrients and oxygen are coming out over here. Urea and CO2 and waste products are going in here. It's all about numbers. There's no capillary fairy sprinkling magic dust to make that happen. It's all numbers. All right, facilitated diffusion. This is also about solute going from high to low. But instead of going to the lipid bilayer, it's got to go through a specific protein channel. And this is what you're looking at. Potassium ion, even though it's potassium, it's with a K, that also has something to do with its Latin name. Okay? And you can see it going through a protein channel here. This is going in the opposite direction, it's going from top down, but that means with these little red balls, there's more red balls up on top and less on the bottom. It's still going from high to low, but it's got to go through a protein channel. Okay? All right, now let's go back. Look at this whiteboard right here, what I've written down so far. Look at that. Everybody look at the whiteboard. I connected the small uncharged things to 1 and 2. I connected the hexagon to number 4. Just hold on here. I'm going to get better at this, I promise. All right, everybody see that whiteboard? Now look at this animation we started with. Diffusion. Facilitated diffusion. Never goes through. If this little arrow was water, not soluble water, osmosis. Facilitated diffusion. Never goes through. Everybody got this animation in your head? Look at the whiteboard again. See the connection? Do you see why I bothered to get my ass out of bed and come down here to the campus and use the whale room? So I can use 3 banks of whiteboards? You know why I do this when I don't have to? Because my students last semester, the second half of spring, told me that this was still really effective. That's why I'm doing it. Okay. Let me get this back to. All right, so we got to facilitated diffusion there. Now let's talk about active processes. And I'm only going to give you one today. It's called active transport. You need to know something about ATP here because cells that are doing active processes are burning up ATPs. And even in this whiteboard that I'm doing, I'm utilizing an outline arrangement. And in the case of active processes, it is also going mostly low to high concentration, up or against the concentration gradient. Put the camera back on. You've seen this enough, but right now, before I put the camera back on, look at right in the middle of this figure, because I need to explain this. Okay. I think this extension cord is going to work, actually. All right. So on that slide is active transport. A little bit later, in physiology, there's two different types of active transport we go over. But I think next week we're going to talk about bulk transport. I'll put this on the whiteboard now. And there's two different subforms of bulk transport. Looks like I need a new blue pen. You have things that move in called endocytosis. There's three subforms of that. This is why you need to be organized with the content. Why am I able to remember this without looking at notes? Because it's organized in my brain. And when you organize it in your brain, you know it. And the reason why I want to put it now is because I also want to connect the dots to that animation. I'm getting noise. Hold on. Someone operating a leaf blower. Gotta love that. Because bulk transport is actually how you get these large things to go in and out of a cell. And it does so in a way that does not require it to cross the plasma membrane. That's why I wanted to add that on there now. Okay? So let's talk about ATP. I think I'm going to put that on this far right side. You guys want to know about ATP, or do you guys want to just read it in the textbook? It'll be really easy if you guys just read it in the textbook. Easier for me. You guys want me to explain ATP?
Yes.
Yes.
Ugh.
Explain it to us.
I'm going to talk about the 4 biologically important macromolecules next week. One of them is nucleic acids. And the way to understand large macromolecules, the 4 biologically important macromolecules, is think of them as huge chains. If you can't imagine a chain, imagine your necklace is a very delicate chain. And it's made up of these little circular metal rings that are interwoven called links. So you got chains and links. ATP is an RNA link or nucleotide, and it has to have 3 things. Hopefully you can see it here. You have to have a nitrogen-containing base. In the case of ATP, it's adenine. That's where the A comes from. It has to have a sugar. In this case, it is ribose. That's why it's an RNA nucleotide. If this was deoxyribose, it would be a DNA nucleotide, but it's not. It has 1 more oxygen.
Just a little bit cut off on our end.
What's that?
We can only see the A part.
Oh. Better?
Yes, much better. Thank you.
All right. Now you have to qualify as a nucleotide, you have to have a nitrogen-containing base, a sugar, and at least 1 phosphate group. In the case of ATP, it has 3. In fact, that is the name abbreviated, adenosine triphosphate. It has 3 phosphate groups. I just put a P with a circle for the phosphate group. Everybody got it? The energy is found in the covalent bonds between the phosphate groups, these purple lines. That's where the energy is found. The reason why is because a phosphate group is covered with oxygens. And as we saw with water, oxygens are highly negative on the outside, and it's like putting 2 negative ends of a magnet together. It takes a lot of energy to do that. So let's see if I can do it down here.
It's a little blurry. What's the word in the pentagon?
Ribose.
Ribose. Thank you.
It'll focus up when I get out of the frame. It's the camera is focusing on my focal length, not the whiteboards. Okay. So this is ATP, 3 phosphates. This is ADP, 2 phosphates plus phosphate here. And then the little I means inorganic phosphate because it doesn't have carbon. And basically what is going on constantly in your cells is you're doing this cycle. When you break that bond, energy is released to do work. And you could think of it as energy out. When you put that last phosphate group back on ADP and make it ATP, this has to be energy in from food. That's why you got to constantly eat. All right, let me get out of the frame and maybe it'll come into focus. Does everybody see that? Let me move the camera close. Yeah, that looks pretty good. Is that pretty sharp?
Yes.
Everybody see that?
Thank you.
Okay, now let's switch back to the PowerPoint. Does this not make sense, what's going on in the middle? ATP is breaking down into ADP plus PI. That's providing the energy to pump uphill. See these little gray balls? There's more out here, less in here. Active transport is going uphill from low to high. And it's got to break off an ATP to do it. Okay. Look at this animation here. If I can get it to recycle. There's less calcium ions on the bottom. It's going to burn an ATP to put it on top where there's more. It's going from low to high. Oops. Takes a while to reset these things. But now you understand what that ATP going to ADP plus P. Everybody got it? So when we talk about cellular energy, it's talking about burning an ATP. Boom, all done. Any questions? I'm going to go ahead and pan the whiteboard. This is the right screen. Let me stop this. This is the right whiteboard. Boom. In the future, when I'm not providing a Zoom recording, you might have to screenshot these at the end. Here's the middle whiteboard. And here's the left whiteboard. And that is week 1. All done. Any questions before we stop this?
Yeah, I had a quick question
Hey.
just regarding, so when we were talking about the lipid bilayer and the diffusion and osmosis processes, so when something crosses the lipid bilayer, so obviously the top of the lipid bilayer, you said it was polar and the middle of it is non-polar,
Yes.
and then on the other end of it is again polar. So does that mean only polar molecules can pass through that lipid bilayer?
No, in fact, that's a good question. If you look at those figures of the phospholipid bilayer, the heads are tiny and the tails are long. That means that the width of that plasma membrane, of that phospholipid bilayer, is actually largely non-polar. The tails are way longer than the heads. The only reason why water can go through those tails is because it is so small and uncharged, and it doesn't just flow right through. Because of those tails, it goes through with some difficulty, but it does go through. Osmosis is slow because of the thickness of those tails, okay? But that also means, and I'll bring this to clinical relevance as well, steroids are hydrophobic. They are non-polar. They're basically built off of a fatty acid. Basically one of these tails. They just, and cholesterol, same way. That's why cholesterols are all part of all cell membranes, okay? So when a few years back, women were suffering from osteoporosis and their doctors were prescribing them hormone replacement therapies of the yin yang, and it was estrogen, and the bones were better. The women actually looked and felt younger. Everybody was happy. The only problem is because hydrophobic, non-polar thing.
This law seems to know, like,
Mute yourself. Mute yourself.
this girl just sent this over 3 days ago.
You gotta mute it.
Can you repeat that again? Because I couldn't even hear somebody's
You're muted.
microphone's on.
When they gave them estrogens, it's a steroid, it went through all your trillions of cells. And the amount of side effects happened, especially in the cardiovascular system, were grave. And they had to stop doing that. They still do hormone replacement therapy, but they do it for a specific medical reason, not just because someone wants to look younger and I don't want to get osteoporosis. What was used to be standard of care is now malpractice because of the fact that steroids can cross any cell membrane because it is hydrophobic. Okay. Any other questions?
Yes. Besides for lab after this, for me at least, what should we have read, prepped, and gone through for next week's lecture?
For next week's lecture, as soon as I get to my office, I'm going to post the week 2 PowerPoint.
Okay. So let's go through that.
It actually shows you what sections of the textbooks are relevant. You can go ahead and read through those.
Okay.
Any other questions?
Do we need to prepare anything for today's lab?
No, not really. Just have the laboratory objectives is all. You need to have that.
Okay.
You want to get into the habit of preparing for labs. It's just that at this very first class, we're not expecting students, especially in the first week, to be ready.
Okay.
Okay? Any other questions? Can you tell I want to get out of here and end this meeting? That's what an introvert does. Okay, guys. Have a good weekend.
You too. Thank you so much.
Thursday lab, I'll see you in lab at 1 o'clock.
Thank you.
Thank
Okay.
you.